Hey guys, today we're going to be going over Kinematics topic 1.2, representations of motion in 2D kinematics with Arya and Jamal, who's going to be our person in who we're going to use to demonstrate different problems. Okay, so if you don't know already, you can watch our topic 1.1 video for introduction to kinematics, the basic formulas, the whole shebang, basically kinematics in one dimension. Now, we're going to be going over kinematics in 2 dimensions. So, let's say in basically projectile motion. So, the problems we experience now is a car or any object moving in one direction in just the x direction or the y direction, or a projectile moving in the y direction. Like maybe a ball we throw up, or a person you throw up, like Jamal. Now, we're going to combine these two and have a projectile or some object moving diagonally at a certain angle, x, or let's use theta. Now, you might, at a certain velocity, usually, especially in kinematics. Now, before we start, let's draw a free body diagram for this ball. What are the forces acting on this ball? As we went over in video 1, the only force or acceleration that you see in kinematics problems is gravity. So this has a force of gravity on it, which means it's going to feel an acceleration down of 9.8 meters per second squared. Always, especially in these projectiles. Now, a key thing to notice is that this acceleration is only downwards, so it's not going to affect the movement in the x direction. Or the only thing that's being reduced is the y direction. So what we're going to do is we're going to split this problem up into the x and y directions. Bear with me here. Let's say we have a ball and it's up at a direction of 30 degrees at a velocity of 50 meters per second, diagonally. Now, let's make a triangle and represent this using vectors. We have a velocity of 50 meters per second on this diagonal at an angle of 30 degrees. We have an x component here, or let's call it y component, and an x component here. What we're going to do is approach this problem separately in the x direction and separately in the y direction. The x direction and the y direction have no correlation with each other, and they act completely independently. However, the object's motion is a combination of both these. So how do we solve for y here? Well, if you remember your trigonometric identities, you know sine of an angle theta is equal to the opposite side to that divided by the hypotenuse of the triangle. In this case, if we take 30 as theta, we get sine 30 of 30 degrees is equal to the opposite of this angle, which is y, divided by the hypotenuse of 50 meters per second. So we get the y component of our velocity is equal to 50 sine 30 meters per second. That means our object, even though it has a sine of 30 is equal to roughly 1 over 2, so y equals 25 meters per second. So while our object does have a velocity of 50 meters per second this way, it's moving up at a velocity of 25 meters per second. Now we can do the same thing to solve for x, as we can use our cosine theta identity, because cosine of theta is equal to adjacent divided by hypotenuse. Theta is 30, and our hypotenuse is 50 meters per second. So the y direction is equal to, the x direction is equal to 50 cosine of 30 degrees. And cosine of 30 is root 3 over 2. So we get x is equal to 25 root 3 meters per second. So this object is moving at 15 meters per second at an angle of 30 degrees. At the same time, it's if we break down this, we have a component of 25 meters per second upwards and 25 root 3 meters per second to the left. Now, let's say someone asks you, what distance does this object, let's draw this again, object 30 meters per second. Let's draw this again, and let's say I ask 30 degrees and a velocity of 50 meters per second. Let's say I ask you, what distance x does this travel? Well, what would you need in this scenario? Well, let's just forget about this, and let's just say we have a one-dimensional problem with a object moving in a direction at a certain velocity. And if I ask you for the distance it travels, well, we know that x final is equal to x initial plus plus velocity times time. And if we subtract x initial to get the change in position, we get delta x is equal to velocity times time. So not only do we need the velocity in the x direction, because this problem is moving in the x direction, we also need the time that it travels at that velocity. Well, now remember how we learned that gravity is only affecting the vertical direction. So if there wasn't any gravity, the ball would just continue up, and away into space to another planet. However, there is gravity. So gravity is going to pull this the ball down, and eventually it's going to come back to the ground when the force of gravity goes against the initial velocity. Okay, so now what we need is the velocity and the time. We already solved for the velocity in the x direction. We got 25 root 3 meters per second. 25 root 3 meters per second. Now we need a time. And now we know, while we did break up the problem in the x and y directions, we broke it up in the x and y directions, the time is constant for both of these. Because once the object hits the ground, the velocity is going to be 0. So, if we know that we can't figure out the time in the x direction, because the only thing we have is the velocity in the x direction. However, in the y direction, not only do we have the initial velocity, we also have the acceleration that's acting on it, which is 9.8 meters per second squared, or gravity. And the initial velocity in the y direction is 25 meters per second. So, if you remember from our previous video, the formula for the velocity final is equal to v initial plus acceleration times time. Now, let me ask you a question. When is the velocity in the y direction going to be 0? Or when does the object stop moving in the y direction? Let's just draw the trajectory. At this point, the object has a velocity of 0 meters per second in the y direction. Because if I freeze time at that point, the object is just staying still at the top until gravity starts accelerating it downwards and eventually it comes down. The only reason it stays in motion this way is because there's no force acting against the velocity in the x direction. So it's going to continue its trajectory if there wasn't any gravity. So we know that right at this point right here, the velocity final is going to be 0. So we can plug that into our formula. V final is equal to 0 meters per second, which is equal to the initial velocity of 25 meters per second, plus the acceleration, which is negative 9.8 because it's opposing the direction of motion, squared, times our time. So now if we solve this equation for t, we'll get the time it takes for the projectile to move this amount of distance. So we move 25 to the other side, subtract 25 meters per second from both sides. So you get negative 25 meters per second is equal to negative 9, let's just round it up to 10, negative 10 meters per second squared times time. Divide both sides by negative 10 meters per second squared. The meters cancel, the seconds cancel. We're left with 1 second at the bottom. So we get negative 25 divided by negative 10 or 2.5 seconds, equals the time it takes for this object to move this amount of distance. However, if you recall in the problem, it was asking for the total distance. Well, since gravity is constant, the time it takes for the object to reach its main point is the same time it takes for the object to reach the next point. Sorry, let me just turn on Do Not Disturb. Cool. So we can multiply the time by 2 to get the total amount of time, because the time it takes for the object to reach the vertex or the highest point when the velocity in the y direction is 0 is the same amount of time it will take for it to come back down. So we multiply 2.5 by 2 to get 5 seconds as the total time of the trip. Now we solve for the time, so we can simply go back to our initial formula of change in the x direction, or the distance it travels is equal to velocity times time, or velocity in the x direction. This was 25 root 3 meters per second. And the time, as we solved over here, is 5 seconds. So we can multiply these to get just the change in x. The change in x would be the seconds cancel, so you get meters. 5 times 25 times root 3, which is 125 times root 3 meters. Cool. That's kinematics in 2 dimensions. Let's do one more practice problem. Let's say there is a mountain and we push off